Good day to you all. Evan Snowman here for Umughloko, making the difference. Today we're looking at Pythagoras' theorem, or the Pythagorean theorem as some people prefer to call it. It's again one of my frustrations that we, in so many times in the junior grades, give you information to use, such as we saw earlier with the similar triangles, but we wait all the way till the senior grades to actually prove those theorems to you. And many of you will have seen some very interesting proofs about the Pythagoras theorem. I've even seen one that uses a water in a rotating triangle. You have a look on YouTube for it. It's a fascinating little proof. But today we're actually going to prove Pythagoras theorem to you for the first time formally in your school career. And so what I'd like to do is consider a right angle triangle. And so what I have here is a right angle triangle in its Greek orientation with the hypotenuse at the bottom, and I'm going to choose to label it ABC. And what you'll notice is that although it is right angled, there's an extra line drawn in here. It is the altitude that is resting on the baseline here that I've got, which in this case actually happens to be the hypotenuse, and we're going to call this point here where the altitude intersects the base, point D. And what we're going to look at is similarity in the three triangles that are in the diagram. What I'm hoping you can see is that there actually are three triangles in the diagram. There's the left-hand one that I've shaded, the dotted one on the right-hand side, but there's also the entire triangle ABC. And if I was to take any pair of these triangles, I could actually prove that they are similar, because if this is x, and this is a right angle due to straight line, then this will be 90 minus x, which makes this one x, and makes this one 90 minus x. So it is not difficult to show that these three triangles are similar to one another, and so therefore that triangle ABC is similar to triangle DBA and is similar to triangle, if it's ABC, DABC, it will be DAC. As a result, if I was to take the first two, and I was to look at these two in combination, I would see that AB over DB is equal to BC over BA, which leads to an interesting result that therefore AB squared equals BC times DB. Again, I'm just going to simply rewrite it as DB times BC, because I've got a bit of a personal preference for writing it that way, and I'll show you what I mean by that now. This is a very interesting proportion that we get from looking at those left-hand pair, and that is that the left-hand slant side, in this case AB, that side squared is the left-hand piece of this base hypotenuse times by the entire hypotenuse. And that's quite interesting. And it might transpire, or might interest you to see that if I was to do this, repeat this for the right-hand one, this one squared would equal the right-hand piece times the entire length. And I hope that you can see that by looking at the outer pair over here. And if I look at the outer pairing here, I'm going to get that AC over DC equals BC over AC, and therefore we get that AC squared equals BC times DC, or as I said to you, my personal preference, DC times BC, the part times the whole. So we have a very interesting proportion here that where we've got AB squared equaling a product, and we've got AC squared equaling a product. We will use this in the next slide to actually formally prove Pythagoras' theorem. Some of you guys might be able to see where this is heading by just looking at the sum right now. However, what I'd like to do is I'd like to look at what happens if I look at these two. And if I look at those two, I'm going to get that DB over DA is equal to DA over DC, which will also equal to BA over AC, but I'm not really fussed about that one right now, so I'm not actually too fussed about this one actually at the moment. I'm also in the left-hand pairing that I've just described, and as a result, I'm going to get that dB times dC equals dA squared, and this is called the mean proportional for right-angled triangles. Effectively, that d, the center line squared, is the left-hand piece times the right-hand piece. Now these questions don't occur often, but they occur often enough that they are a little bit infuriating because we forget the importance of this discussion we've just had here, how easy it is to do this using the proportion theorems. Now, we can go and prove that the triangles are similar right from the get-go, and actually you know, use more time than we necessarily need to in an exam, and therefore be slightly inefficient. These theorems are well enough known that you could actually just use the three that are labeled here at the bottom, that AB squared, there we go, AB squared is that AC squared is that product, and dA squared is that product. Now, what I'm going to do is I'm going to look at this for Pythagoras' theorem, and as I said, use the idea of similarity and similar triangles to prove Pythagoras' theorem for the first time to you. So, were I to take a blank triangle again and to relabel it the same way that I did last time, such that I have A, B, C, and D, we had from the one thing that AB squared equaled BC times BD. From the other one we had that AD squared, sorry, again, my apologies, I'm going to quickly fix my mistake. Again, it was that these things were that was C over there and that was D over there, my apologies. Okay, it's BD times BC, that AC squared equals CD times BC. Okay, so as I challenged you just now, what would happen if I took these two and I added them together? Because after all, we know that Pythagoras' theorem says that we add these things. So AB squared plus AC squared would be the same as BC times BD plus CD times BC. We have a common factor here in BC. So if I took BC out as a common factor, I'd have BC times BD plus CD. But I hope you realize, you can see that BD plus BD plus CD is nothing other than BC in its entirety. So I now have BC times BC, which can be written in abbreviated form as BC squared. And I've now gone ahead and proven Pythagoras' theorem. That actually for me is quite amazing that we started out by showing it to you in grade 8, and we did it with numerical examples, and we waited 4 whole years to actually prove it to you. And I'm sure that some of you guys may have been curious enough to go and investigate it and find out other proofs for it. There have been proofs lying around since about 2000 BC already, all over the globe. This is the first time that you formally in your schooling have encountered it. Here is an example I found in the C. Ruler textbook. Okay, B is a point on the circle centered at O. BD is perpendicular to AC. So in many ways this is the same picture as what we had previously, except for the fact that there's a circle around it. BD is the midpoint of the radius OC. If the diameter of the circle is 24, find the length of BD. Leave your answer in simplified third form. I like that last hint. It does tell you that the answer won't be a perfect whole number, that there will be either a decimal, but they have instructed you to leave it in third form. So they have given you a hint that the answer will not be a perfect, nice whole number. Okay, so let's go read through it. If the entire length is 24, then we know that we have a radius, which means that AO is 12, and that the entire length of OC would be 12. But if D is the midpoint, that means that this is 6 and this is 6. And as I said, from the mean proportional in a right angle triangle, albeit that this case they've labeled the vertices in a different order from us just now, we should be able to remember that BD squared will now equal AD times DC, and that is the proportion theorems for right angle triangles. Okay. And as a result, we're getting that BD squared equals 18 times 6. I got it right? Yes, I do. 18 times 6 is 108. So therefore, BD squared will be, sorry, I need to rewrite that. BD is going to be the square root of 108. Not BD squared, just BD. And I need to write that in simplest third form. So what's that going to be? Well, that is 27 times what? I don't know right now. 9. Okay, so we can take 4 out of it. So it's 4 times 27, which is therefore 4 times 9 times 3, which gives us 3 times 4, sorry, lies. Apologies, trying to write too fast at this point in time, which is going to be therefore 2 times 3 times the square root of 3. So in simplest third form, it will be 6 root 3. I think with one more example, let's have a quick look and see what happens next. An example I found from a very old textbook in the years before they gave you diagrams. Well, I don't think that's too difficult to realize that if the problem is that there's no diagram, the solution is quite apparent. Draw the diagram. So we have a altitude to the hypotenuse of a right angle triangle. I'm going to choose to draw the right angle triangle in what we in modern society consider to be standard form. So with a right angle at the bottom right, not as we had drawn in the two previous examples with the hypotenuse being a base side. Okay, they tell us that the altitude drawn to the hypotenuse. So again, there is some language here that we need to make sense of. We need to know what an altitude is, and we need to know what it means to be drawn to the hypotenuse. And so when we think about it, an altitude is a height. It is always perpendicular to its base. A triangle has got 3 altitudes, but they're telling us specifically that this one is drawn to the hypotenuse. So they are talking about this line here, and it is at right angles to the hypotenuse. Okay, and it does so in such a way that it breaks the segments into the ratio of 1:4. Okay, that is a ratio, not a length. They then tell us that the length of this altitude is 8 units. So again, please note that as in a previous example, I'm choosing to mark the ratios without any unit symbol, and therefore to distinguish between it, I'm actually writing the lengths with a unit symbol just to make sure I clear out what is a ratio or proportion value with an actual physical length. Okay, and just now they gave us lengths of the base in the previous example, and also to find the length of the altitude. This time they give us the altitude and also to find the length of the base. So we now know that if we would put labels into it, and again I'm going to choose P, Q, R, and S, just to have different letters, we know that SQ squared is going to equal PS times SR, but we know that PS is 4 times the length of SR. So if we were to plug these various concepts in here, I've got 8 squared equals 4SR times SR. So 64 equals 4SR squared. 16 equals SR squared. So 4 equals SR, and 4 times that, which is 16, will equal PS, which is the actual answer to the question that they're asking, because the question they asked is what was the length of the longer leg, and the longer leg here is 16. Okay, so here were two fairly unusual examples using the Pythagoras theorem and the proportions that come out of Pythagoras theorem. They are worth knowing if you've got the inclination to study extra maths, but they can also be found during the exam if you were to choose the correct two triangles and prove similarity from the get-go, and take the time to do that. Okay, fairly short and sharp, but a very, very important theorem that we've gone and proven. We've actually gone and proven for the first time that Pythagoras' theorem a squared plus b squared equals c squared is in fact correct. Thank you for your attendance today. All the best.